I'm going to give an overview today of the small cell forums. It's 5G API for small cells. So this is an initiative that the Small Cell Forum kicked off about 6 months ago to define this 5G API, and we're due to get this document published within June. So I've been the technical lead for that item within the Small Cell Forum. I'm also employed by Intel, and my day job is actually working in the area of 5G virtualized RAN. So what is the 5G API? So it's part of 5G FAPI. 5G FAPI is a set of common APIs that the Small Cell Forum defines, and we do that for the key parts of a small cell. And the overall motivation is to really helping create a vibrant ecosystem for small cells. So in order to create the API, what we do is we get together a collaboration of different hardware vendors and software vendors and system vendors, and they come together and they actually define that API. That kind of grouping of people comes about from the way small cells are typically formed. Historically, you have a small cell vendor, and they put together their small cell from a collection of parts that come from different hardware and software vendors. So if we all work together with a set of common APIs, then we end up with an interchangeable set of parts that are available for small cells. So the purpose is then that we get to encourage that competition and innovation that's going on within the industry. If the system vendor wants to adopt the latest innovations in like silicon or software or some new 3GPP feature, then that's obviously going to help them, and it's going to minimize the amount of custom engineering they have to do. And then if you have a new entrant into the market, if there's an API that they could just build their product to, then they can immediately become part of that interchangeable set of parts. So we've been doing this for a while in the Small Cell Forum. It started over a decade ago when we produced a 3G PHY API. The really key one that's been developed in the past is the LT PHY API. That was released publicly in 2008, so it supported the basic release 8 version of LTE. And then over the last decade, that's been slowly, widely adopted in the small cell industry, and we now support the more sophisticated features. So we support narrowband IoT, we support LAA with that particular LT FAPI. And then so 6 months ago, as Release 15 got finalized, it really became logical for the Small Cell Forum to expand that and start working on the 5G FAPI. And as I mentioned at the start, that should be available for everyone to read in June. So where is FAPI located? So this diagram is the 3GPP's impression of a 5G network. So we have our AMF, our UPF, so that's our 5G core. And then we've got our G-Node B, our base stations that are making up our RAN. And within that base station, we, as mentioned quite often, we have this disaggregation, so we have CUs and DUs, and 3GPP do actually specify one interface there, F1. From a logical perspective, if we look inside the base station, then we've got our stacks, so our layer 2, layer 3, our MAC, the RLC, the PDCP, and the RRC functions. And then underneath that, we have layer 1, so the PHY and the RF. So it's different levels of expertise that you need for those two different parts. So the layer 2, layer 3, they're protocol stacks, so it's a classical protocol stack that you need to get developed for that. And then obviously layer 1's a PHY, so it's typically signal processing expertise that you need there. So FAPI is located between the two, as that's kind of a logical way where you might actually bring together components from different companies. So pulling out exactly where FAPI is, FAPI, going back to history again, when over a decade ago, a group of companies in the Small Cell Forum at that time, they got together in a room, they stood in front of a whiteboard, and they basically drew what a small cell was made from. And for each of those different components, they started labeling interfaces, so P1, P2, P3. Over the history of FAPI, that's been refined. So now we've kind of identified which are the key interfaces that we can really help by defining. And we've ended up with 4 today. So we have P4. This sits between our control, our SON, so the self-organizing network part, and connects to an NMM, a network monitor mode. So the idea is that NMM can sniff around and look for 2G, 3G, 4G, and 5G cells around, report back information to the SON, and then the SON's got a really clear view of what the radio environment is around it. We have P5 and P7. These are the two interfaces that are part of the PHY API, so I'll come on to them more later. And then we have P19. So this is to control the RF in an integrated small cell. So 5G PHY API, one of the key philosophies, and I think one of the reasons why it has able to be successful, is that we make sure that this interface is abstracted from the underlying architecture. So you might build your PHY. It could be virtualized on general purpose compute. It could be from an SoC. It might be from different components such as FPGA. And we intentionally ensure that we're abstracted from that. So we don't favor one type of architecture or another, but we're really trying to make it a level playing field for all those architectures to really support innovation. We split our control interfaces into that control plane and the user plane. So P5, these are our control messages. The purpose of these is really to configure the PHY and move it from idle to be running, and when it's running, it's giving a small cell service. But then we need to have our P7, so our user plane interface. So as well as transmitting the data, the nature of 5G and OFDM is that we have to send hundreds of parameters to really explicitly define what's going to be transmitted and received across the air interface for every single subframe. So the bulk of the 5G PHY API is this P7 interface, and that's sent on a per slot, per TTI, per subframe basis. So I wanted to step back a bit from the architectures and the low level of the PHY API and really say what 5G features are we trying to ensure that we enable and support well in the 5G PHY API. So it's really when you take those headline 5G statements about what it's going to do for us, they're the ones that we inherently kind of focus on. Not all of those are applicable to the PHY, so I've pulled out 3 of the key ones that are. So first, it's always said that 5G is going to give us increased capacity. And from a PHY perspective, that means improving our RF utilization. So we have our new techniques, we have massive MIMO, and we have beamforming. So beamforming in particular is something that can be done in many different ways, and so we need to ensure that that API can support fairly basic beamforming to quite sophisticated ones. And so it's important to make sure that's very flexible in the API. Then we have increased bandwidth. So we're going to have more bands. We've got sub-6 gigahertz and all the reuse of bands and new bands down there. And then we have millimeter wave, which is inherently a small cell. There are certain PHY features that are specific to sub-6 gigahertz or millimeter wave, but we don't want to have different APIs for each, so we need to make sure that that's all thrown in one common API. And then finally, the low latency that's always talked about for 5G. So there's the classical new URLLC service. So some of that low latency is going to come from edge services, but there are features that are in the PHY to help enable and support that. So typically it's called like mini slot and preemption. These are features that we need to make sure that our PHY API supports. And then there's also the sub-carrier spacing we have in 5G. So there's different options. We can have a sub-carrier spacing that means we end up with the same subframe as an LTE, so every 1 millisecond. But we can also have sub-carrier spacings that go down to having subframes as often as 125 microseconds. So we need to work with those different types of frame pairs with our PHY API. There's been a lot of talk about disaggregation. And I need to apologize to Rich, is that sometimes I put on here DU, where he says I should have put RRU. But I wanted to just highlight what the 4 key ones were. So we have our split 7-2X. So this is the one, the low-level split that's being worked on by the O-RAN Alliance front haul and is well adopted. So in this case, we actually see that FAPI is located within that central unit. We have split 6. So here, between the MAC and the PHY, FAPI actually has to spread across that interface, and that's the work that the small cell form does in terms of network FAPI to enable that. And then we have split 2. So split 2 is what you get in sort of 5G non-standalone networks with the F1 interface, and so here FAPI is now in our distributed unit. And finally, if you've got that distributed small cell, we still have FAPI inside it. So if you're an operator, you'd probably be most familiar with FAPI in terms of split 6 and when it's spread across the interface. But in all those different disaggregation architectures, we have it there inside a component, just ensuring that we can get that good interchangeable set of parts. Yeah. So really kind of highlighting where FAPI is going to be where we have small cells. So they're sort of pretty much everywhere and do everything in 5G. So we can have our sub-6 gigahertz, we can have millimeter wave, We can have those networks indoor. We can have outdoor small cell networks. Small cells are viewed as kind of key for increasing the extra data we're going to get from smartphones, with eventually having kind of network densification. So we need to ensure it's going to help enable eMBB going forwards. And then we have our new vertical segments. So we have URLLC and we have IoT. These are quite often going to be enterprise small networks. And so here again, it's something that we need to make sure the PHY API enables. So the reason of showing that is really to say what parts of Release 15 do we support. And the basic summary is everything. There's so many different architectures that we need small cell for, that we need to support all of that. And while initial small cells may not use all those particular features in Release 15 to start with, it's more likely to be a slower rollout and adoption. If we want to enable innovation, then we need to make sure that right from the beginning, it's everything that we actually support. So I pulled out 4 kind of high-level ones that are key and have probably been the hardest for us to get right in the PHY API. To carrier aggregation, we had that in LTE. We've still got it in 5G, so we need to have a scheme that is supported. Then there's beamforming. So I mentioned that beamforming has many different options. We can have different numbers of layers. We can have different numbers of antenna ports. We can have different numbers of antennas and panels. And we can use various types of beamforming, different ways of calculating beam weights to do that. And so you need to allow people to have sort of quite a basic beamforming scheme to actually having quite a sophisticated one. And so that's been quite key to try and work on and get right. And then we have bandwidth parts. So this is related to the subcarrier spacing. It's not just the entire cell that can operate on different subcarrier spacings. We can actually have them mixed and matched together. So we can have part of our bandwidth operating on, say, a 1 millisecond periodicity, and then we can have to have another part operating on, say, 250 microseconds. So we need to have the flexibility to mix and match and have that API exchanging messages at different types of periodicities for different parts of the cell. And then finally, we come to the flexible slot format. So this is a TDD, and in LTE for TDD, there were various fixed different patterns, but that's much more flexible in 5G. So we need to really allocate the fact that the next subframe can be anything. It could be a downlink, it could be an uplink, it could be a mix. And so that's kind of a key aspect for the flexibility side. So I really just want to reiterate that this work is almost complete, and we should be publishing it in June. So what's next? So the next thing is really that view to go and look at split 6. So now we have done that work on the PHY API, we can actually look at extending that across that particular split. So the motivation for this is really to enable FAPI across a non-ideal backhaul. If you have an ideal backhaul, it will work as well, but we do the work to ensure that it will work across non-ideal. Again, it's this collection of system vendors, software vendors, and hardware vendors that we bring together to do this. I've shifted the order around a bit because this time it tends to be system vendors that really take the lead on this, as it's a complete self-contained box that we're linking together. So the motivation this time is to get this virtualized ecosystem going. So we end up with this converged approach towards virtualization. We can have scalability with a CU connected to multiple DUs, and those DUs coming from different vendors. So that helps with interoperability. Plus, additionally, you do get some centralization benefits. You can have some pooling gains. The fact you might have things like centralized scheduling, that can all enable to make your network more efficient. So the diagram of our 5G network FAPI, one of the key things about network FAPI is you end up with exactly the same bandwidth requirements as F1. So you have tighter latency restrictions, but the bandwidth doesn't increase dramatically between the MAC and the PHY compared to between the PDCP and RLC. We want to make sure that NFAPI allows one CU. It's got to connect to multiple DUs. As those DUs now physical boxes, they might well not just have one carrier inside them, but they might have several carriers inside them. So whereas FAPI is traditionally been a one-to-one match, so one MAC, one PHY, now we really need to handle the fact there'll be one CU, multiple DUs, and in that DU, multiple PHYs. So there's some extra complexity to add there. Then we have to handle the fact that we can have different latencies between each CU-DU pair, and need to manage that in a coordinated fashion. And then, of course, we're going to have jitter on those connections. So most of those additions for network FAPI is very much a wrapper around FAPI. So FAPI is still there in the heart, and then we just do the work to extend that across an actual interface. So that's the work item that is intended to be doing next, and we will always be looking for companies to come and contribute in that area. Okay, so I think that's the end of my slide. Thank you.